This tutorial is for 6th grade, Module 4, Lesson 9. In this lesson, we're going to look at exponents and how variables can be shown using exponents as well. To begin with, we're going to review the powers of 10 and how we can express them using exponents. You can see that I have three forms of a number. I have the standard form, the expanded form, and the form of the number expressed as an exponent or as a power of 10. If I look at the number 100, 100 is the same thing as 10 times 10, and it's also the same thing as 10 to the second power. The number 1000 is 10 times 10 times 10, and we can show that as 10 to the third power. The exponent is telling me how many tens I multiply to get the original number. The number 10,000 can be expressed as 10 times 10 times 10 times 10 in expanded form, and as an exponent it would be 10 to the fourth power. And the number 100,000 would be 10 times 10 times 10 times 10 times 10, which is also 10 to the fifth power. Question B says, what is the connection between the expanded form version of the number and the exponent in the power of 10 version of the number? So if I look at the expanded form version of 100,000 and look at my exponent, the number of tens that are being multiplied together is the same as the exponent in the power of 10. Since I had to multiply 5 tens together to get 100,000, we can see that it matches the 5 as an exponent. In 10,000, I multiplied 4 tens together, and that matched the 4 in the exponent for that number. So there's a good connection between the expanded form and the exponent when we write those powers of 10. We'll use those same ideas when we represent other numbers that are not 10 in exponential form and simplified form. Question A has 3 times 3 times 3 times 3 times 3. So if you remember when we did powers of 10, the 10 was the base, and in this case my 3 will be the base. The exponent tells me how many 3's I'm going to multiply. Since I have 5 3's in my expanded form, we'll say that that's the same as 3 to the fifth power. Now, to find the simplified version, I need to multiply all of those 3's together. So I'll multiply 3 times 3, which is 9, times 3, which is 27, times another 3, which is 81, and times one more 3, which is 243. So that means the simplified version of 3 to the fifth power is 243. In question B, I have 11 times 11. So 11 is the base, and I'm multiplying two 11's together. The simplified version would be 11 times 11, which is 121. Notice that to find the simplified version, I'm not taking 11 times 2. That's a common error when working with exponents. We don't multiply the base times the exponent. The exponent tells us how many copies of the base we're multiplying together. Question C, we have powers of 10 again, so I have 10 as my base, and I'm multiplying 5 tens, so it's 10 to the fifth power, and that was 100,000. In question D, I have a combination. I have several 8's that I'm multiplying and a 5. Now I can't combine the 5's and the 8's. So we'll say for this one that I'm multiplying 5 times 8 to the fourth power. To simplify it, I need to figure out what 8 to the fourth power is first. Well, 8 times 8 is 64. 64 times 8 is 512. 512 times 8 is 4,096. So I need to take 4,096 times 5 to come up with my simplified answer. And that is 20,480. So you can see how quickly these numbers get big when we're working with exponents. Question E has a fraction that we're multiplying. I have 4 copies of 2/5 that I'm multiplying together. So I'm going to write the 2/5 in parentheses and then put the exponent outside of the parentheses. So I had 4 groups of 2/5 that I'm multiplying against each other. I put it in parentheses to make it clear that the exponent is for the entire fraction, not just for the numerator or for the denominator. Now to simplify my answer, I'll start with the numerator. Well, 2 times 2 is 4, times 2 is 8, times 2 is 16. So the numerator is 16. For the denominator, 5 times 5 is 25, times 5 is 125, times 5 is 625. So the simplified version is 16 over 625. Now let's move on to expressing exponents that have variables. The first question shows me r times r times r times r. So r would be my base because that's the number I'm multiplying each time, and my exponent would be how many r's I'm multiplying together. So the exponent would be 4, r to the 4th power. We don't have a simplified version of this because we don't know what the r stands for yet. In question B, I have the number 5, and then I have a series of g's, or the variable g, that I'm multiplying. I cannot combine the 5 with the g, so I have to keep them separate. So we're going to multiply 5 times g to the 1, 2, 3, 4, 5, 6 to the 6th power. So 5 times g to the 6th power is the exponential form. Remember, when we have a number right next to the variable, that means that we're multiplying those. We don't need to put the dot in between those to show multiplication. In question C, I have an A and a series of B's. Again, we'll show the A separately, and then we'll show the B as the base and the power of 5, because there's 5 B's that they're multiplying. So a times b to the 5th power would be the exponential form of this expression. In question D, I have 2x that I'm multiplying by 2x by 2x. So again, I'm going to put the 2x in parentheses and put the exponent outside of the parentheses to show that it's not just the x that's taken to the 3rd power, it's the entire 2x that's taken to the 3rd power. And finally, I have 3 a's that are multiplied together, and then we'll multiply that against 4 b's. So we'll say a to the 3rd power times b to the 4th power. And again, since we write those right next to each other, it's implied that they're being multiplied. We don't have to put the dot in between them. In this section, we're reviewing the term square numbers. I have some diagrams here of the number that we would call 3 squared, 4 squared, and 5 squared. When we have a number that has a 2 for the exponent, we can read that number as 3 to the 2nd power, or we could say 3 squared. Same thing with 4 squared. I can say 4 to the 2nd power, or I can say 4 squared. And I could say 5 to the 2nd power, or I could say 5 squared. If you notice, each of these diagrams is actually a square because the length and the width are the same. So 3 times 3 is the same thing as 3 squared, and that gives me a product of 9. Here I have a diagram that shows a variable being squared. We can refer to this as x squared because it's x to the 2nd power. The question is, what's the dimensions of this square? Well, x squared would be x times x. That means that the length and the width of my square would be x. So if we have x times x, the answer would be x squared. Just like we have square numbers, we also have cubic numbers. And cubic numbers can be expressed as multiplying 3 numbers which makes sense because when we worked on volume, we multiplied the length times the width times the height. So 4 cubed can be shown as 4 to the third power because it's 4 times 4 times 4. In the next diagram, the dimensions of the cube are 5 units. So we can show the volume of this cube as 5 times 5 times 5. And as an exponent, we would say that that is 5 cubed, or 5 to the third power. Here we have a cube whose sides are x units long. In order to find the volume of this cube, we would say x times x times x, length times width times height. And as an exponent, we would write that as x to the third power, and we could also express that then as x cubed. So using exponents with variables is similar to how we use exponents with regular numbers.